Okay, Assalamu alaikum warahmatullahi wabarakatuh. Welcome back. And today we are talking about force, mass, and acceleration. This is week 8, and we are going to be getting quite familiar. We're going to be getting quite familiar with Newton's laws of motion. Um, so let's just get right into it because we will be talking about laws of inertia. We'll be talking about real life problems as well. So, as always, I would like you to have your calculator ready, have your pad and paper, and we are going to be solving some problems. Please make sure that you pause the video and you try and give those problems um, a good try yourselves before you actually look at my solutions. Okay? Right. So, let's get on with it then. So, Newton's laws of motion. So, there are three laws of motion that Newton has come up with. And basically, the first one is known as the law of inertia as well. The second law is the one that links them all together in a formula known as force equals mass times acceleration. And the third one is perhaps the most well known one that simply states force. For every force, there's an equal and opposite force. Okay, for some reason, people seem to be quite familiar with that one. So, who's this Newton fella anyway? So, basically, Newton is the scientist. He's a physicist, actually, and he's considered a bit of a legend. Um, as to whether the whole thing of the apple falling on Isaac Newton's head actually happened, that seems to be not exactly historically accurate. In fact, although Newton himself mentioned it in his memoirs, how he observed an apple falling from a tree and how this inspired his thoughts on gravity, there's actually no evidence, as far as I know, that it actually hit him on the head. Okay, so the story likely gained some popularity because it kind of illustrates how everyday occurrences sparked his groundbreaking work on gravity. In reality, though, I don't think Newton actually developed his theory in a few days. In fact, I know it took him years to develop his theory of universal gravitation, drawing on numerous observations, of course, and mathematical insights. And if you want to be pedantic, you could talk about his fourth law, which is the law of gravitational force between two masses. But we are going to be talking about the three laws of motion and only the three. Okay, so basically, force is linked to mass and acceleration. So if we look at this formula here, which has become quite famous, hasn't it? I mean, you see it all over the place. You can see that force is linked to mass and acceleration in this format. So what does this mean? This means if for an object to have acceleration, it has to have a force acting on it. In order for an object to have force acting on it, you have to have acceleration. These two are linked together. So you can't have one without the other. Not only that, they are directly proportional. So what this means is if I increase the acceleration, I increase the force acting on an object, and if I increase the force acting on an object, I increase the acceleration. Okay? And of course, mass is rather essential. Now, we will be talking about mass a bit more as we discuss the first law of motion, which will happen now. Okay, so Newton's first law of motion basically states that an object does not want to change what it's doing. Simple as that. An object does not want to change what it's doing. If an object is staying or standing still, then it wants to stand still. It's not going to move. There's a catch though. Unless an external force is acting on it. And likewise, if an object is moving, it's not going to stop unless an external force acts on it and stops it. Okay, that's quite simple, isn't it? I mean, we already know that, don't we? If you leave if you leave an object sitting on the table, right? If I leave these glasses sitting on the table, and then I leave the room and I come back and I see that the glasses have moved, that defies physics. Okay, it really does. In fact, it completely goes against Newton's first law of motion because this object should not move unless an external force moves it. And that external force could be anything, could be another person. Okay, so I'll be asking, who took my glasses? Or it could be a ghost, if you believe in that, or it could be anything, right? So as long as an external force acts on it and moves it, okay, it's not going to move. Likewise, if an object is moving, it's not going to stop unless an external force stops it. So what about here on Earth, though? Because these laws are made for anything to be true anywhere, as far as we're concerned. So if I roll a ball here on Earth, if I roll a ball, what's going to happen to the ball is after a while it's going to stop. It's not going to roll forever. It's going to stop. Why does the ball stop? Well, the ball stops because if I roll a ball and it stops eventually, it's going to stop because of friction. And friction in this case is the external force, right? So there's always going to be an external force to stop the object. Otherwise, it's not going to stop, right? And the other way of thinking about this is if you think about something in outer space, like a meteor or a shooting star, it's going to continue moving, or a planet or a star, whatever it is. If it's moving in outer space with no air resistance whatsoever, if it's moving which of course it's moving constant speed, if it's moving, it's not going to stop unless something hits it, okay? And that's because there's no air resistance, right? And that is exactly what we're talking about with Newton's laws of motion. An object that is sitting still is not going to stop moving, and an object that is moving is not going to sit still unless an external force stops it, or and unless an external force acts upon it and gets it to move or stop, right? So that's the first thing I need you to know. So an object at rest remains at rest as long as no net force acts on it. Okay? And an object moving with constant velocity continues to move with the same speed and in the same direction as long as no net force acts on it. Now, here's the other thing as well. Now, if you notice here, force is actually going to be a vector, right? Because acceleration is a vector, displacement is a vector, velocity is a vector, acceleration is a vector, momentum is a vector, force is a vector, right? So force equals mass times acceleration. This is a constant. Acceleration is a vector, therefore this is a vector. Both of these are vectors. Forces are vectors. Now, because forces are vectors, we can add them. But we'll come to that. So anyway, Newton's first law, also known as the law of inertia. Why is it known as the law of inertia? Well, I'm about to explain. The law of inertia simply states that an object doesn't want to change what it's doing. Now, I want you to think about that. If an object is small, let's say, for example, a mouse, okay, and a mouse is moving along and you want to stop the mouse, you're going to apply a little bit of force, right? And you can quite easily stop a small mouse if you apply a little bit of force. Now, if we change that mouse to an elephant, of course, the elephant has significantly more mass than the mouse does. And so what do you think is going to happen? You're going to need a lot more force to stop the elephant, okay? And so that is what's known as inertia. Inertia increases with mass. Inertia is the resistance to change. The elephant has a lot more inertia than the mouse does. The elephant has a lot more resistance to change. Both ways, by the way. If the elephant is not moving and I try to move the elephant, oh boy, that's gonna take a lot of force. And if the elephant is moving and I want to stop the elephant, once again, that's gonna take a lot of force. And that's because the elephant has a lot of inertia. And I want you to think of inertia as resistance to change, okay? And the mouse has less inertia than the elephant does. Okay, so that's what inertia is. Resistance to change. Resistance to change. Okay, that's what inertia is. Resistance to change, right? So we've discussed the law of inertia. We've discussed Newton's first law. Let's put it into action. Now, I've got a couple of scenarios here, and they're quite interesting scenarios. Now, the first scenario says, I would like to tighten this joint between the wooden handle and the hammer head. So I've got a hammer head over here, and I've got the wooden handle, and I would like to make that joint, tighter, okay, fit in a bit more snug. Now, I've got two options here. I can drop the hammer on its head, or I can drop it on its handle. Now, which one is going to result or yield better results? Which one is going to make that You're gonna make that joint, really nice and tight and snug. Okay, well, does it make a difference even? I want you to think about that for a second. I want you to pause the video. I want you to give it a good thought, and I want you to unpause the video and listen to the explanation. Well, turns out it does make a difference. Look, obviously the hammer has a wooden handle, while the head is usually made of iron or some sort of iron alloy, which is quite heavy, obviously. So this is going to have a bigger mass than this part here, which is going to have a small mass. And why is that important? Well, if I drop the hammer on its head, like I'm doing here, the mass of the handle, the smaller mass, is going to be pushing down into the hammer or the hammerhead, and that's going to really, it's going to result in some sort of tightening. But of course, by now, hopefully, you should have figured out that if I drop it on its handle instead, this here, this here hammerhead is not wanting to stop because of the law of inertia, right? It wants to continue moving down, and it's got a big mass. So what it's going to do is it's going to push further down than in this scenario. The handle is not going to push further as far down as the hammerhead is, because the hammerhead has much bigger inertia due to its bigger mass. Okay? So that's that situation. It's very interesting. That's where we use Newton's laws. We use them in everyday life, and we use them obviously to design things in engineering and technology. Right, what about this guy here? What's happening over here? Well, over here we've got a scenario where some interesting person has thought, well, I've got an anvil and I've got two bits of string. One is holding it from the top and one is holding it at the bottom. And the person comes along and quickly jerks it down. Okay, so just tugs down on this string. And basically the situation is such. We're trying to figure out what's going to happen if the person suddenly pulls on that string real fast, okay, in a quick jerking motion. What's going to happen? Is this string going to break first, or is this string going to break first? Okay, basically, are both going to break? What's going to happen? So once again, I'd like you to pause the video. I want you to consider the laws of inertia, and I want you to consider the mass of this anvil, and then unpause the video and listen to the explanation. Well, turns out there is a difference, okay? And if the person pulls on the string rather quickly, what's going to happen is this anvil is not going to want to move, especially since it's happened quite quickly. So what is going to happen is it wants to stay where it is, right? If it wants to stay where it is, it means this string is going to break first, okay? Now, if the person pulls on it slowly, it's going to give it time to move, and that one is going to break first. But if the person pulls on it rather quickly, then what's going to happen is this is going to break first. So that's what's going to happen here. As long as the person pulls on it rather quickly, then this here will break first, and the anvil will not fall down on the person. Okay? Once again, it's because of the law of inertia. This here is very heavy, and it doesn't want to move, and that's what's going to happen. And it might be a little bit hard for you to understand, so I would urge you to actually try this experiment. And you don't have to try it with something super heavy. What you can do is you can actually try it with an apple or an orange. Okay, tie an orange, both with a string on both sides, a string that is not very strong, so you can break it, and tie it up, and then quickly pull down on it and see what happens. Physics works. Okay, force and acceleration. As we've already mentioned, force is actually a vector. So what that means is you can add forces. So if I have a force acting on an object, let's say, for example, this box, and somebody's pushing it, so the push force of about 15 newtons, and then somebody comes on this side and pushes with a force of 30 newtons, then the overall force, what we call the net force, is going to be 20 newtons that way. 20 newtons that way. The reason for that is because we can add forces. And likewise, I'll do another example. If there is a box on the table and somebody comes and pushes with 50 newtons and another person decides to come and help them out and they push with a force of 40 newtons, then the box will move with an overall net force of, hopefully you can do that, 90 newtons to the right. Okay? That is what we're talking about over here. Okay, and hopefully this makes sense. It's really quite similar to what we did with velocity and displacement as well as acceleration. Okay, let's do question 8 here. Suppose that two spaceships have engines that produce the same constant force. However, one of the spaceships has a much smaller mass. Which spaceship would have the greater acceleration? Well, we can actually do that right now. So we've got two spaceships, and I'm going to try and draw two spaceships, and I'm going to make them face this way now. Okay. It's not the best drawing, okay? But here we go. We've got two spaceships. And so one of them looks like that, apparently. And the other one looks like that. And they both have the same size engine, okay? I want you to imagine that they both have the same size engine. But obviously, this one has a much bigger mass. So this one has a mass of 200 tons. 200,000 kilograms. Well, this one here has a mass of 50,000 kilograms. Okay. And they both have the same engine that produce the same force, constant force. So the force is going to be, let's say 50,000 newtons. And this one produces 50,000 newtons as well. Well, we can tell that the acceleration is going to be rather different because force is equal to mass times acceleration. And, well, in this scenario over here, we have acceleration is going to be equal to force over mass, because obviously this is what we have over here if you prefer triangles. So acceleration is equal to force over mass, which is going to equal 50 over 50. So in this case, the acceleration is 1 meter per second squared, and it's going to be moving forward. While in this case over here, the acceleration is going to be 50,000 over 200,000. Hopefully you know that that is 1/4, or 0.25 meters per second squared that way. So you can see how they're related. So acceleration is going to be inversely proportional to the mass. Okay, inversely proportional to the mass. So as the mass increases, the acceleration is going to be decreasing. Okay. Right, the second law. And we've already covered this one actually. So force is equal to mass times acceleration. As you increase the force, you increase the increase the acceleration. Excuse me. And if you increase the acceleration, you increase the force. And of course, if the mass is more, then you're going to need more force, and produce more acceleration. Sorry, and you're going to produce less acceleration if the mass is more, because that is the formula that links all three. Let's do some problems to make sure we understand that. And then a 1,800 kilogram car has an acceleration of 3.8 meters per second. What is the force acting on the car? Okay, so here is the car. I always like to draw a diagram, even if it's a really badly drawn one, but at least it makes things a little bit more visual. Okay, it's just easier to understand. Here is the car, 1,800 kilograms. The acceleration is going to be 3.8 meters per second squared, and we are looking for the force. Of course, by now we all know how force, mass, and acceleration are linked. Force equals mass times acceleration, so it's going to equal 1,800 multiplied by 3.8, which is, should be able to do that in my head, or 7,000 something, and 8 times 3.8. It is going to be 6,840 newtons. Okay. Next, once again, I would like to remind you to please do these yourself before you look at my answers. Is it possible for an object at rest to have one force acting on it? If yes, provide an example. If your answer is no, explain why not. It's quite tricky, this. So let's think about outer space. Outer space with the stars and everything else. If an object is floating in outer space, let's say this asteroid over here, and there's a single force acting on it, is it possible for it not to be moving? No. The reason for that is because, well, if there is a force acting on it, then it's going to move in that direction. Simple as that. Okay. So what about here on Earth? Okay, let's say a car. A car. Okay, this old Figo. And there is a force acting on it, and this force is acting on it this way. Well, only one force. It's going to start moving, isn't it? What about if the force is acting on it this way, but it's going to start moving? But what if it's sitting on the ground? Then really, there's two forces acting on it now, because there's a force of pushing down, but there's also a reaction force from the ground. However, there is actually a scenario where it is possible for an object to have one force acting on it and yet be stationary. And that is going to take us back to projectile motion. Remember what I said when you throw an object up in the air? Let's do that again. Whoop. Throw an object up in the air. What's going to happen? What's going to happen is the object is going to fall back to the ground, right? But right in the top here, right at this point, the velocity of the object is going to equal 0, this magic number that we're looking for. And yet the acceleration is always acting downwards, 9.81. So in essence, there is a force acting on this object, which in this case is going to be a ball. And the force is the force of gravity, and it's pulling it down. But at this very moment, right at the top there, it's going to have a stationary position. It's going to be completely not moving, stationary. And yet, it has a force acting on it. The force hasn't changed. There's a force acting on it downwards, but at that very moment, that one moment, it's going to be stationary. So that is the only scenario I can think of. Okay, it's basically when an object is in projectile motion or right at the top of its parabola of movement, and then it's going to have momentary moment of stationary non-movement while still having a force acting downwards on it. Okay, interesting, isn't it? That is a very interesting question. Right, question 2 says you push a 12.3 kilogram shopping cart with a force of, let's draw a shopping cart. Let's see if I can still draw a shopping cart. Yep, that's about what a shopping cart looks like. Okay, and of course they usually have like a thing down here and like wheels, and you can put the eggs over here. Right, so this has a mass of 12.3 kg, and you push with a force of 10.1 newtons. What is the acceleration of the cart? The acceleration of the cart is going to be simply force equals mass times. Oh, let me just draw the triangle. Sometimes it's easier for my students to visualize things with a triangle. Force equals mass times acceleration. And so acceleration is equal to force over mass, which is going to be 10.1 over 12.3. And that is going to be 10.1 over 12. It's about 0.8. So 0.82 meters per second squared. That is the answer. Let's look at B. If the cart starts from rest, how far does it move in 2.5 seconds? Well, that is very interesting. So we can actually use delta D equals VIT. We don't need that because it's starting from rest plus half AT squared. We've got the time, 2.5 seconds. VIT is not necessary because it says starts from rest, so VI is equal to 0. And so this whole thing is going to be equal to 0, right? So it's going to be delta D equal to half multiplied by the acceleration, which we just found. Yay, how convenient. 0.82 multiplied by um, 2.5 squared. And that's going to equal something like 4.5 meters or something. Always try and guess an answer, like even if it's like 1 or 2 3 points off, it doesn't matter. But just to get an idea of what the answer should be, like you should always try and have a guess in your head. So this is about, oh sorry, half of that. So 2.5 squared, so about 5. So it should be about 3 meters or something. And I got 2.56 meters in the positive direction. Okay, great. That's what that is. Next, battery-powered lawnmower has a mass of 52 kilograms. Okay, lawnmower. I like drawing things. Okay, I just really like drawing things. Um, and sometimes just doodling, right? So, lawnmower means grass. So I'm gonna draw some grass too. Here we go. That's a battery-powered lawnmower, and net force on the lawn the mass is 52 kilograms. The force is equal to 44.5 newtons. What is the magnitude of the motor's acceleration? Well, that's easy. Nope, other way around. 44. Just be careful with your with your arrangements. Over 52, and that equals 44.5 divided by 52, and that equals 0. Oh, no. 0.86 newtons. Not newtons, meters per second squared. Because we're looking for acceleration. Okay, there you go. I push you, you push back. Now we're talking about Newton's third law. So how are we doing for time? Okay, not bad, not bad. 27 minutes. So Newton's third law is perhaps one of the more famous ones. And all it says is that for every force, there is an equal and opposite force. Okay? For every action, there is an equal and opposite reaction. Okay? And so if you're pushing this table, the table is pushing back on you. If I'm standing on the ground, okay, here you go. I'm standing on the ground. There is a force acting down on me if I'm standing on this ground. And this force is known as weight force. And it is caused by gravity. Right? Now, this weight force is acting downwards. Now, in my case, that's about 800 newtons, let's just say. And then there is a force that is acting upwards. Now, how do I know there's a force acting upwards? Well, if there wasn't a force acting upwards, what's going to happen to me is I'm going to fall right through the ground, right? So I want you to think about this for a second. If I was standing on water, okay, and what's going to happen is I'm going to fall right through. And that's because there isn't a force acting upwards that could stand my weight force, okay? That's all it means. It can stand or carry my weight force. So if I'm standing on water, let's just forget this for a second. Let's say I'm standing on water, okay? Those are waves. What's going to happen is obviously I'm going to go right through the water. And that's because there isn't an upward force capable of, it's not putting up a reaction force that is equivalent to my weight force. However, if I'm standing on the ground, happily standing on the ground like in the classroom, then what's going to happen is I'm just standing there. I'm not moving. I'm not going up in the air. I'm not going into the ground, which means the ground is carrying me. So even though there's a weight force acting down, pulling me down, the ground is actually pushing back up with the same force as my weight. So it's the same force, but it's in the opposite direction. So if I'm 800 newtons down, the ground is actually pushing up with 800 newtons up. That's it. Really, that's all it means. Another example is like if you push on the floor, if you punch the wall, you might break your knuckles. And the reason for that is because you punch the wall is pushing back with the same amount of force that you punch the wall with. Okay? That's what we mean by equal and opposite force. It's the same magnitude, it's just in the opposite direction. What if I was standing on the table? What if I decide to suddenly stand on the table? Now, that is possible, right? I could stand on the table, no issues. right? Especially if it's like one of those good tables, like, solidly built tables. If I stand on the table, what's going to happen is nothing. I'm just going to stand on the table. The reason nothing happens is because the table can withstand the force of my weight. So as I'm pushing down, the table is actually pushing up. Now, what happens if an elephant stand on the table? Or what happens if two or three people stand on the table? Okay, so instead of one person, we now have like three funny looking dudes standing on the table. And one of them is really quite big too. Okay, now what's going to happen in this case is obviously the table will not be able to put up a force equal to the weight force of all three people. And what that results in the table, sadly, breaking, because the table has to put up a force equal and opposite to the weight force, otherwise it breaks. Otherwise it breaks. And then the floor goes, I can do it. I can put an equal and opposite force. So that's the way physics works. All right. So Newton's third law: for every action force acting on an object, there's a reaction force acting on a different object. Okay, interesting. And the action and reaction forces are equal in magnitude and opposite in direction. Okay, so here's an example of what that looks like as well. Is I've got a fridge and I'm pushing on the fridge and the fridge is pushing back. Well, and of course that force can also be resistance in this case. Um, this is actually how we move forward. This is how we're able to move. If you wanted to move, right? If you wanted to walk, the reason we're able to walk is because you push down on the floor and therefore you launch yourself forward. Okay, now that might be a bit hard for you to understand. Well, let's think about a different example. Let's say here is a frog and the frog wants to jump. Now, how does a frog jump really? And I don't think I've ever drawn a frog before. Here's a frog, happy frog. Okay? And the frog wants to jump up in the air. What does the frog have to do in order to jump? Well, turns out the frog has to push down on the floor in order to push himself up in the air. Okay? For every action, there's an equal and opposite reaction. The frog wants to push himself up in the air, so therefore he has to push down on the floor really quite hard. Okay? Ooh, interesting. Let's do a problem. What force must be exerted on a 1,500 kilogram car to make it move with an acceleration of 3.8? Force equals mass acceleration. Let's fix that. Force is equal to mass times acceleration. So 1,500 multiplied by 3.8 because it's mass and acceleration, and that's going to equal approximately 5,000 something. 5,700 newtons. Question 2 says you pull your sister on a sled across an icy, nearly frictionless surface. All right, let's have a look. Here's the sled. Here's your sister. And here you go. She has beautiful long hair. And she's smiling. And you are pulling her. Here we go. You are pulling her this way. This drawing, this is a very interesting drawing. Here we go. But you're a good older brother. And so you're pulling your sister. And you're doing it with a smile. You're pulling her this way with a horizontal force of 120 newtons, which is not much. The sled has an acceleration of 2.5 meters per second squared. If the sled has a mass of 7.4 kilograms, what is the mass of your little sister? It's very interesting. So we're going to ignore all of that for now, and we are going to work out what is the mass using this force and this acceleration. So this is how I would do this. I've got the force, I've got the acceleration, so I need to work out the mass first. So force is equal to mass times acceleration, and so mass is equal to force over acceleration. Okay, mass is equal to force over acceleration. Here it is, over here. Oops. Excuse me while I find where we were. Oh, we've done quite a bit, actually. Here we go. So force mass is equal to force over acceleration. So I've got 120 over 2.5, and that's going to, don't start. Sometimes it does that when it gets a bit warm. So hopefully it won't do that. That equals 48 kilograms. Now, out of those 48 kilograms, remember the sled is actually 7.4 kilograms. So I still haven't found the sister's mass. So the mass of the mass of sister is going to equal mass of sled plus sister minus mass of sled. So it's going to equal 48 minus 7.4, and that equals 41.6 kilograms. No, it's not. It's 40.6. 40.6 kilograms. Okay. Right. Let's keep going. Oh, let's talk about momentum. Momentum is quite fun as well. So momentum is another vector quantity. And momentum is, remember how we said force is equal to mass times acceleration? Well, it turns out if we change acceleration to velocity, we now have another quantity, and we call that momentum, right? And momentum is this p, and it's a small p actually, and it's Latin, and that's why, even though it's a small p, we call it momentum. Right, and we can actually use this to rearrange Newton's second law. Because, well, how do we do that? Well, let's have a look. Knowing that now there is another quantity called momentum, and it equals mass times velocity. And let me just explain something about momentum. Momentum is basically like oomph. Like, when things are moving, you know how we said they have inertia? And momentum is basically like when something is moving at constant velocity. If it's heavy, if it's got a huge mass, right, then it's going to have a high amount of momentum, and it's not going to want to stop. You might have heard that before. Like trucks have a lot of momentum, and so it's hard for them to stop, especially if they, if they're like, 18 wheelers or something. Now, smaller objects or objects that don't have a lot of mass have smaller momentum. And so momentum has to do with the mass, and it has to do with the velocity. If something is moving at high velocity, then it has a lot of momentum. So let's say, for example, a small bullet. A small bullet that weighs about 20 grams. So a small bullet isn't going to hurt anyone if I just throw it at them. But a small bullet that's fired out of a chamber with gunpowder, then obviously it's going to travel really, really fast. It's going to have a huge momentum because the velocity is really high. So even though the mass is quite small, the velocity is huge. And so it's going to have a big momentum enough to kill someone. Likewise, a truck that's moving really, really slow, okay, still has a lot of momentum because it has a lot of mass, okay? So momentum has to do with mass and velocity. It's inertia in motion. It's inertia in motion. It's resistance to movement while moving in motion, okay? Right. So let's come to this guy now. Now, where did we get this from? Newton's second law states that force equals mass times acceleration. How do we get from there to here? Well, remember acceleration is equal to change in velocity over time, and momentum equals to um, mass times velocity. So if we change acceleration to acceleration equals change in velocity over time. Now remember that velocity over time. So I can do that instead. Mass equals mass times velocity over time, right? Well, it turns out mass times velocity, that's equal to P. So force is also equal to P over time. Okay, so those are now the three triangles that we need to know about. I'm going to draw them. I'm going to draw the three triangles. Okay, so don't panic. But these are the three triangles that we need to know. So the first one is force equals mass times acceleration. The next one is the one we just found. Force is equal to momentum over time. And the third one is the one for momentum that states that momentum equals mass times velocity. Okay? So those are the three triangular formulas. Okay, let's do this here. Pause the video, try and give it a go yourself. A 71-kilogram parent and a 19-kilogram child meet at the center of an ice rink. Okay, let's see if I can draw this one. Should be interesting. They place their hands together and push. If the acceleration of the child has a magnitude of 2.6 meters per second squared, what is the magnitude of the parent's acceleration? Okay, so this is ice here. Smooth ice. And this is the parent and the child putting their hands together. And what's going to happen is the parent is going to push the child, and the child is going to push the parent. Now, it turns out this here child has a mass of 19 kilograms, and this here parent has a mass of 71 kilograms. And the acceleration of the child is going to be 2.6 meters per second squared. So what is it asking for? It's asking for the magnitude of the parent's acceleration. Well, where do we start? We start with this guy here. Force equals mass times acceleration. But do we have enough to go on? Indeed, we do. Because what we need to understand, boys, and anyone else watching, is that for every action, there is an equal and opposite reaction. So once we find the force of the girl, then we can find the force acting on the parent because they are equal and opposite. So the force acting on the girl is going to be 19 times 2.6, which is going to be 19 times 2.6, which is going to be 49.4 newtons. Now, that is going to be equal and opposite. So it's going to be negative 49.4 newtons. Now, somebody might be going, hang on a minute. Why did you decide this was negative and this was positive? It doesn't matter. I could have decided that this was negative direction, and then that would be negative. As long as I remember that this is equal and opposite. So this now becomes positive. So as long as you have them equal and opposite, it doesn't matter, right? So here we go. So that's 49 and that's negative 49. So now I've got the force and the mass for the parent. So what can I do with this information is I can find the acceleration, because acceleration is going to be force over mass, and it's going to be 49.4, 49.4, not 4.9.4, 49.4 all over 71. So it's going to be a smaller acceleration, obviously, because it's, well, a bigger mass. So generally speaking, this mass here is about 3.5 times the mass of the child. So it's going to have 3.5 times less than the acceleration of the child. So the acceleration of the child is 2.6. The acceleration of the parent is expected to be around 0.7 or 0.75. Okay, 49.4 divided by 71. 0.7. So almost on the dot 0.7 meters per second squared. Okay, assuming that's negative 2.6 because she's moving away. This is going to be 0.7, and they're going to be moving that way. Two groups of canoeists meet in the middle of a lake. After a brief visit, a person in canoe 1 pushes on canoe 2 with a force of 46 newtons. So that is a force of 46 newtons over here. To separate the canoes, the mass of canoe 1 and its occupant is equal to 150 kilograms. And the mass of canoe 2 and its occupants is equal to, so let's call that M2, let's call that M1. And that is equal to 250 kilograms. What are they wanting? What they're wanting is the acceleration of each canoe. So this one's quite easy to find out because the acceleration is going to be, that's the force. So the acceleration is going to be, excuse me, let me just, here we go. Force equals mass times acceleration. And so it's going to be 46 over 250 because we've got the force, we've got the mass, and we need the acceleration. Oh no. Here we go. So it's going to be approximately 0.18. Seconds squared. What about this one here? Well, we know the force is going to be equal and opposite. So this force here is going to be negative 46. We've got the mass as well. So the acceleration, once again, is equal to force over mass. So it's going to be negative 46 all over 150. And so I expect that to be approximately 0.3 or negative 0.3, 46 divided by 150. And that is negative 0.31 meters per second squared. Hopefully that wasn't too hard. Okay, your 1,400 kilogram car and I'm going to make it a pickup truck because I think I've always secretly wanted to get one. I don't have one. Just think I've always wanted to get one. Right, anyway, so that is the pickup truck. Not a very good, not a very well drawn one. Anyway, so that is the pickup truck that I could come up with at this stage. So that's okay. And this is the trailer. And this is the trailer. The trailer has a mass of 560 kilograms, while the pickup truck has a mass of 1,400 kilograms, or the car, I should say. What is the net force exerted by the car on the trailer? Well, force, mass, acceleration. So it's going to be, well, we're not concerned about the mass of the car in this case because why aren't we though? Like, think about it. If you're pushing on a bag of sand, or if you're pulling a bag of sand, doesn't matter what your mass is when you're doing the calculation. If you're trying to find the force exerted on the bag of sand, it doesn't matter who's the mass of the person pulling. It doesn't matter the mass of the elephant pulling. What matters is the force exerted on the trailer. So in this case, the net force exerted by the car on the trailer is going to be 560 multiplied by the acceleration, and the acceleration is going to be 1.85 meters per second squared. And the acceleration here is obviously the same because they are attached, meters per second squared. So the force acting on the trailer is going to be 560 times 1.85. And that's going to be 1,036 newtons or 1 kilonewtons. What force does the trailer exert on the car? Well, we know it's going to be equal and opposite. So it's going to be pulling on the car. Well, why is it pulling on the car? Think about it. If you are pulling a bag of sand, the bag of sand is dragging you. It's kind of pulling back. It's not helping you push it, right? It's not helping you along. It's pulling back. So it's kind of like, oh, I'm pulling the bag and the bag is pulling me back, right? So it's going to be the trailer is doing the same thing to the car. The car is pulling the trailer, but the trailer isn't making the job of the car easy because it's got mass and therefore, okay, it's going to pull back and the force of the trailer is exerting on the car is going to be equal and opposite. So that's going to be negative 1036. That one is 1036. The last one says, what is the net force acting on the car? Well, the net force acting on the car is going to be mass times acceleration over here. So it's going to be 1400 times 1.85, and that's going to be 2590 newtons, right? Because this is the mass and this is the acceleration. Another way of doing it is by taking the total mass of the system, which is 1400 plus 560, and that's the mass of everything, okay, multiplied by the acceleration, which is 1.85, and that gives me 3626. But that's the wrong answer. Why is that? Because I forgot to take away that. So I need to take away the force that's acting in the opposite direction. So we've got this much force going forward, but we also have this much force acting backwards. So if I add these two together, 3626 minus or plus negative 1036, then it gives me the same answer, 2590 newtons, which is exactly the same as this answer over here. Physics works. Physics works. Okay, and we've got a question here about momentum. Let's have a look. At a city park, a person throws bread into a duck pond. 2 4 kilogram ducks and 7 kilogram goose paddle rapidly towards the bread from opposite directions. So we've got the goose is moving this way. She's quite a big goose, and we've got 2 ducks coming in this way, right? And what is happening if the duck swims at 1.1 meters per second, which is what we have over here, and the goose swims with a speed of 1.3 meters per second? Find the magnitude and direction of the total momentum of 3 birds. Very good. Okay, so in this case, we're using momentum equals mass times velocity. So the first thing is we need to calculate the momentum of the goose, which is equal to the mass of the goose multiplied by the velocity of the goose, which is going, saying goose, it's kind of weird, goose, all right. So it's going to be 7.6 multiplied by 1.3, and that's going to equal 7.6 multiplied by 1.3. And that's going to be 9.9. What's the unit for momentum? Well, turns out the unit for momentum is going to be kilograms dot meters per second. Why is that? Well, I should have talked about that earlier. Momentum equals mass times velocity. And so the unit for momentum is going to equal the unit for mass multiplied by the unit for velocity. So it's going to be kilograms dot meters per second. That's the unit for momentum. So kilograms dot meters per second. What about the ducks? The ducks have their own calculation. So the ducks have momentum of duck equals mass of duck multiplied by velocity of the duck, which is going to equal 4 multiplied by negative 1.1. Why negative? Because it has to be in the opposite direction. Remember, it's a vector. This is going this way, so it's 1.3. That one's going that way, so it's negative 1.1. Now, I could do it the other way. I could make this negative, but then I would have to make this positive, and the results would be exactly the same. Okay? So negative 1.1, and that should equal 4 times negative 1.1. And that should equal negative 4.4. Now, of course, there's 2 ducks, so I got to do this. So again, it's exactly the same. I'm just doing it the long way so people understand. And this is duck 2 now. And once again, it's exactly the same. So all I had to do was really just multiply by 2. So this is duck 1, duck 2, and we've got the goose. So duck 1 and duck 2. So the total momentum of the system is going to be if we add all the momentums together. So the total momentum, P total, is equal to P goose plus P duck 1 plus P duck 2, which is going to equal 9.9 plus negative 4.4 plus negative 4.4, and that is going to equal 1.1. And 9.9 minus 4.4, and that equals 1.1 kilograms dot meters per second. And if you really want to be pedantic, you can go like that. Okay, hopefully that wasn't too hard. I hope you give this a go yourself. Just to summarize Newton's 3 laws, they are Newton's first law, the law of inertia, or the law of not wanting to change. And that is an object will remain as it is, doesn't want to change what it's doing. If it's sitting still, it wants to stay sitting still. If it's moving, it wants to continue moving unless an external force acts on it. The second law says force is equal to mass times acceleration. That's how they are related. As long as you increase the acceleration, you increase the force. And if you increase the force, you increase the acceleration. The third one says Newton's third law states that for every action there is an equal and opposite reaction, which means if you are pushing down on an object, the object is pushing back on you. And of course, we talked about momentum as well, which is equal to mass times velocity, and it's measured in kilograms, not meters per second. Okay. I hope this was informative. Take care.